Hey everybody, John Grimsmo here, and welcome back to Knife Making Tuesdays. It's been a solid 8 years since we've done one, and we are developing a new knife right now, actually, which we developed 11 years ago on the old Knife Making Tuesdays, and that's becoming a reality. So much has changed in the business. It is a completely different, much more mature beast than it was with young John and young Eric. And I want to bring you guys on the journey, and I want to develop this knife and show you guys how we're doing it, and let's do it. Cue the intro. All right, here we are down on the shop floor. It looks a lot different than it did on our last Knife Making Tuesday. So let's go play on the kern. We're currently making an integral handle. I've chosen to spend the past few months doing the work, not filming the progress. They're two separate things. So I've made a lot of progress, and I'm just gonna try to catch you guys up as much as I can, and then we can wrap up the project together. I can show you guys what's happening, when it's happening, but for now it's a lot of catch up. So right now, we have a handle being cut in a shank vise from a block of titanium. The material is dovetailed so that it sticks in really good, except I made a mistake. And I finally figured out what that mistake was. So like, here's the 3D printed prototype of the handle, right? They're pretty much the same, except at some point, because in the cam file, this model is just kind of floating in space. It can go up and down, whatever. At some point early on, I cut the profile and I did a test slot because I just wanted to prove it. But then after that, I moved the model up a little bit. And I noticed that because here, see if we can get a light on this. This is supposed to be a full radius, but it's really just hitting the corner and the corner, and it's not matching the full radius that I had designed. So I'm like, hold on. And when I was watching the tool cut, it was cutting in air for most of it. And I'm like, something's not lining up, something's not jiving here. And I believe that I had at some point moved the model higher in cam, so it thinks the model's up here, but in reality, the first model that I profiled is still down low. So I goofed, I did half the work before it changed, made a change, did half the work after. So basically this piece is now scrap, I'll have to pull it out. But it did prove some things. It proved that the slot, the high feed milling the slot, like we'll show later, is gonna work really good. It proved surfacing of the outside looks real fine. And it started to prove a lot of things, so I'm very happy. Let's pull this out, let's put a new piece in, and start attacking the next go. So one of the curses of being so driven and so clever, if I toot my own horn, is you sort of formulate an idea, and dude, I designed this knife 11 years ago and I've been wanting to make it ever since. And in that 11 years, I've had a lot of time to think about how I want to make it, how I want to do it, what kind of tools do I want to use, how I want to hold material. And I'm at the point now of reality where it's actually starting to happen. And I'm starting to question those choices. But part of me is like locked in. It's like, no, see it through, make it the way you want to make it, and then evaluate if it works or not, change accordingly. So I'm going to stay stuck in that camp. But I have these preconceived notions, like I'm going to use a chunk of titanium. I want to dovetail the bottom so that it can be held in a vise. And I want to be able to hold it up in space and literally use the 5-axis machine to cut every side of the material. And I want to use a high feed end mill to come in and cut down the slot because I think it'll be great. And then I want to come in and I want to tilt the blade, the handle at a 1.5 degree angle and use a tapered ball nose end mill to 3D surface the inside wall of each side. Maybe this is totally overkill, maybe this is whatever, but that's the full Grimsmo that I've had in my head for a couple years now, and I'm like, darn it, I just want to see it through. So that's where we're at. A lot of different people use different ways to cut this feature. Let's go show you. So when I first got our first big boy machine, the Mori here, I was like, oh dude, we're gonna make this integral, we're gonna make it awesome. That was 9 years ago whenever I bought that machine. check out my pile of old tools for this machine. All right, the shop is kind of so big that I can't find the specific tool that I bought 8 years ago for the Mori, but this will be a good example for us anyway. So this is a brazed carbide indexable slitting saw. I have, or not indexable, I have an indexable one with little carbide inserts that slip into the pocket through coolant. I can't find it. So I bought that 8+ years ago when we bought the Mori, because I'm like, dude, we're gonna make integrals. It's gonna be awesome. 8 years ago, it hasn't happened yet, but it's gonna happen now. But I'm gonna tell you why I don't wanna use this slitting saw now, because I've had that 8 years to think about it. I spent a good $1,000 on that tool that I've never used. Okay, so a lot of people do use slitting saws like this to make an integral. So to do that, you have to take your material and you have to likely hold it in a vise like this, so that, you know, the center line and above is exposed. You don't have a lot of material to grip onto, and a lot of slitting saws have a step in the middle. So you can only go down so far before this is hitting the vise jaws. That's one thing, kind of annoying. It's also kind of its own operation, because you have to hold the material from the bottom, get inside, maybe you can machine the top, and then you got to flip it over and do it. I want to do it all 5 axes because we can. Another reason is this is a big tool. It's a big diameter tool. It takes a lot of horsepower, takes a lot of rigidity, a lot of vibration doing this cut. That's not how I do machining. Very light, very fast, very high efficiency machining kind of thing. So for all those reasons, I just didn't want to. And I've heard of people using these, and whether they do it in one pass, super duper 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 slow, or a million small passes, it still takes them like an incredibly long amount of time. So I didn't want to do that either. And the machine like the Kern doesn't really have the rigidity, the horsepower to properly utilize a tool like this. Our Mori does, but I don't want to do it. So those are the reasons, but you can see why it would make sense. You pick the right thickness and you just machine it away and it could work, but you have a depth limit where you can only go so deep before you're hitting here or here, depending on the saw. And it kind of leaves a gross finish on the inside that's not pristine. So, man, those are the reasons. See my filthy tool. This sat under the exposed stairs at the old shop for 4.5 years that we were there. This is all Falcor hair and dirt and grossness, and probably never going to use it. Might, I don't know. Okay, so I ended up removing the bad one that was placed wrong. That's the problem with doing half the work before and then making a bunch of changes and then doing half the work after, is I changed it out of position and it's no longer good. But I can tell the material is getting a lot lighter. It probably weighs half of what this one does. I spec'd oversized material because, well, so we've got our mini integral, and then we also 3D printed a Maxtegral, much bigger, more Norseman sized, and this material happens to be big enough to make that. I don't really have any plans to make this anytime soon, more of just a future thing. So when I bought 20+ pieces of material, I was like, let's just get it for both sizes. I can remove material to make the mini. But for right now, I'm just focusing on the mini. All I want to make is this. So I'm going to burn through the big pieces, wasting a lot of material, a lot of time. And then when I order more material, I'll get the smaller size. There's a lot of money to be saved and a lot of time to be saved ordering properly sized material there. So anyway, this one is removed. The surface finish turned out stunning. Just stunningly good. This is the same toolpath we use on our smooth Rask handles. We have good history with it. You know, we know that the surface finish here tumbles out beautifully to be literally imperceptible milling lines after tumbling. You cannot see it even under the microscope. I like that. So I'm going to load up this one. Let's go do that right now. Today we will be using the Kern Micro Vario. Open the door. So here we have this Schunk slash Gressel slash Ceratizit vise, which has little teeth in it that are going to hold this dovetailed material. Boom, boom, boom. Now a few days ago I pre-machined all of this dovetail material. We got a clip of that. Did it on our Mori, and only took a few minutes per piece. So that dovetail holds into the vise here. The vise is self-centering. So once I tighten that up, I'm gonna, roughly align it side to side. In the future, I might plan either the water jet or the milling, the dovetail milling, so that it, aligns properly, so you don't have to think about it, you don't have to measure, it just kind of goes in. Maybe it butts up against one side, because there's already enough thinking in this industry. The less thinking I can add, the better, especially for the operator, for me, for whatever. The easier I can make it, the just easier your life gets. So you try to put all your thinking up front so that the next guy, which is usually you, has an easier time. Okay, I'm going to tighten that up. One cool thing that I did, there we go, rotate. Just want to show you this side of the vise. So there's a torque spec for the 11mm screw. So I engraved, it's upside down right now, 11mm, and also I engraved 36 foot-pounds onto the side. I love these visual cues. We have it on the other vices that are in the bottom there, and these vices here, the 5th axis vices actually already have it laser engraved on, which is good for them. But yeah, I wrote 75 foot-pounds on those, 75, 36 on this one. Visual cues are the answer to everything. You don't want to have to think, you don't want to have to look it up, you don't want to have to question yourself, you don't want to have to ask a buddy when you can just have the information at the source. So I've got the material loaded in, the vise is like snug tight, but I can still slide it side to side. So I take my calipers and I measure how far it is sticking out on one side, then I move it over here and I measure how far it's sticking out on the other side, and if it's within a few thou, I'm fine. Otherwise, if it's sticking way out on one side, I'll measure that. I'll see that it's, that much. I'll go over here and I'll see, oh, it's sticking out that much. I can just eyeball it and then do it again. But now it's still sticking out too much on that side, so a little bit more. And I'm doing this, one-handed while filming, so it's not the fastest. A little bit more, but when you're focused and paying attention, this is pretty quick. There you go. You could also go like this, using the back side of the caliper, do it side to side, either way. At some point, I'll get you in with a full screen recording in Fusion and we'll really dig into this. But on the side here, you can see all the tool paths. There's a lot of tool paths that are needed to make this handle. Wow, needed by John Grimsmo standards. I've selected the first chunk here, which sort of shows the kind of the profiling the outside, getting rid of all the junk material. And then this folder here is surfacing the sides. So we're going to come in and we're going to 3D surface the sides exactly like our blank is here. So I have a little bit of time before our 12 o'clock team meeting. So I'm going to do just that chunk, not the whole thing, because I want to be here, I want to watch it. And then we'll do our team meeting, and then I'll come back and finish the rest of it. It's coming good though, so by the end, I love Fusion's in-process stock, which as you click on a toolpath, it literally shows you, what's left, what's happening. It's not the most accurate render, but it's quick, it's great. So I can see what to expect by the end of this. And then the last little bit is going to be tabbing that part off, which will be a hand-finished feature at the end. Since we have fancy kern, we have fancy verification software. This is Camplete, which is, funny enough, was bought by Autodesk a couple of years ago. Camplete, okay, so Camplete is a simulation software that actually posts the code. This is real life what's going to happen, not what Fusion thinks is going to happen. And this has all kinds of collision avoidance warnings built in. It'll tell you if something's going to crash. And it gets close. It gets real close. So this, Fusion simulation is really good, but this tells you if it's going to hit the machine here, like the whole model. And Fusion has this kind of stuff coming in because, like I said, they bought Camplete. But this lets me really crash verify everything that's going on. Although truth be told, most of the time I just pass code through it, don't simulate it, and trust it. Know myself, know my experience, trust Fusion for most things. Experience things that I've done before that I'm just making a tweak, sending it again. I just post through. I use the Camplete as my post, not necessarily simulation software. But something like this, it's a good time. So once Fusion has posted the code, it goes to Camplete, then Camplete posts the code, and then it goes to a file, and then I go to a program called TNC Remo, which is a Heidenhain program, which basically has my computer and the kern live. So here I have a Rask folder, integral folder, random projects, Norseman folder. So I go into the integral folder and I copy this file, drag and drop, there to there, overwrite the old one. Decent file, so it takes a couple seconds. It's literally sending it from my computer to the machine right now, and now it's good to go. Now I can open it and run it. So let's do that real time. Run, program, find integral folder, open 1001. Should be good to go. Cycle start. I'm gonna live here for a little bit. All right, I did tighten and torque the stock. You always got to go through that mental checklist of like, did I do everything? I got to switch hands here. This is not how I normally do this. Okay, so from here we can turn the coolant off. We can verify that it's doing what we think it's going to be doing. I have near perfect confidence in this because I've done this before once. But you never know. Yeah, just tickling the outside. That's what I want to see. I'll turn the coolant on in a second here. That's exactly what I want to see. Just kissing the outside. Nothing weird. It's a bit of vibration on that side. I just want to make sure it retracts, clears. Dude. I mean, clearance is clearance. All right, I think we're good. So the coolant, if you're wondering, it serves three jobs. It flushes the chips away, it cools the tool and the cutting zone and the workpiece, and it lubricates because it's an oil. It's a water-based oil. So it's got those three jobs. All the chips flow down there, goes down a chip conveyor, goes out the back, gets filtered, comes back in, recirculates. Every machine does that here anyway. And then these two machines are on oil, not water-based cutting fluid, so it's like literally feels like cooking oil. It's disgusting. But this is good. This is super good. So all the coolant, all the chips go down to this, which is a chip conveyor, which goes back to the other side. Okay, we're on the other side of the machine. The chip conveyor, it's literally like conveyor paddles that move all the chips this way up into the bucket. The liquid itself, the coolant, goes into this drum. And when my yogurt tub is still holding strong, by the way, from a couple years ago, if you remember that, when this floats up enough, then the pump turns on, which it just did. And now it's pumping the fluid through this hose into our paper band filtration unit. So all that coolant goes through this paper, 20 micron paper, and gets filtered. So whatever chips don't make it into the chip conveyor, make it through here, and then filters, and then we have clean coolant sitting here, quite a huge drum of clean coolant, which then gets pumped, filtered through two bag filters, which we have pressure gauges, in, out, out. And when there's a pressure differential of too much, so we got 40 psi, 43 psi, 45 psi, that's fine. When it starts getting really wonky, then it tells us which bag is clogged and to replace it. And then it gets pumped right back to the machine. It really vibrates on this side of the cut. But it's fine. A I'll give you a little sneak peek at a future Knife Making Tuesday episode. So today we're making the handle, right? I've been working on that for weeks and weeks. The next step probably will be the blade. And to do the blade, we're going to use our Speedio, and I'll show you right now, real quick, how we're making our rasp blades, because we're going to use the same process to make the integral blade. So right now, I won't go too deep into it, because I'll save that for a future episode. But here we have a little tiny grinding wheel that is chop grinding. So if this is the diameter of your wheel, it's literally going up, down, up, down, up, down, up, down, and stepping over a little bit every time, and that's how we're grinding the bevels on our rasp blade. Getting a very good finish. I wish it were a little bit better, but it's completely acceptable and polishes out with our methods perfectly. And we measure, we have this 3D printed checking fixture that tells us this blade is a -1 where this transition line meets to our gauge. Lets us monitor consistency side to side. But the blades start out like this. So this is soft. We soft mill all the features, and then we heat treat them, and then we lap them ourselves, giving that beautiful flat, shiny, shiny, shiny surface. Then the bevels get ground into them, and then they go back to finishing for further polishing. So the integral blade is going to have the exact same workflow. All right, roughing is done. Tool breakage detection. There's a little laser beam that goes in there, checks if the tool length is still the same as it was. Changing to 3/16 high feed de Boer end mill. I love these things. They're absolute rippers. So what we're doing there is we're clearancing, just like on this piece, we're clearancing behind the handle, just down a little bit, ever so slightly. So that when the, imagine if this was your surfacing tool, the surfacing tool can get to the bottom edge of that handle. There's a bit of a clearance down there. That tool makes noise. Flip it over. I don't know if you saw that little rotation. All right, another tool breakage check. Another tool change. It pre-calls the next tool, so it's like ready. There we go. Tilt the pallet at 45 degrees, come in with the ball mill, and start roughing. And then finishing. Meanwhile, it's pre-calling the next tool so that the next tool is ready on the side, so it just makes the tool change a little bit quicker. All right, after the initial roughing contour pass, I did a little pause so that we could get in here and take a quick look. So this is a rough finish at 2 thou per flute, which means you're going to see more scallops as the tool is doing its little cuts. And I'm just ripping. I'm going as fast as I can, you know. And then finishing will be at 1 thou per tooth, which is a really good finish that tumbles out nicely. But I can tell by looking at this that it's a lot rougher finish than we normally do. But it's a roughing pass, meant to hog out the outside skin material. And then this 8 flute Zadaro 1/4 inch ball mill is an amazing tool. I use it now for both roughing and finishing. It just lets you go faster. Okay, so I will undo my pause. It's in single block right now. Go back to run, turn it down, hit cycle start, slowly turn it up, and then always make sure we're at 100%, and it actually says here 103%. There you go, 100%. Just ripping through code. So for finishing, we're going, what, 73 inches per minute? Roughing was closer to 100. Some new carbide turning inserts just came in from Iskar. I ordered these things like a month ago, and they took a month to get here, which I'm not happy about. I'm just trying a new style because on the Williman, which will be a critical part of the Integral project, chipping inserts. So I want to try this different grade, different brand of insert, and hopefully I can do that. Because some of the hardware features, like these little stop pins, on the production knives, they're going to sit flush, obviously, but These 3D prints didn't fully go together properly. So I have to make these fancy little threaded stop pins that go through, and then the button for the button lock, because it's going to be a button lock. So I got to make that, which is, here's a example of what the button lock is basically going to be like. If that's the head, then this is the shaft. It's tiny and spindly. Again, 3D printed and just a bad representation, but still kind of cool to see. And then the pivot and the bearings, we've already made about 100 of them. These are different than our regular bearings and our regular pivots. I mean, very similar, just fatter. Fatter pivot, bigger diameter bearing cage. So we have these. I don't have to worry about those for right now. I can make the first however many bunch of integrals. We have enough pivots for that. So I gotta make button, I gotta make these stop pins. I will eventually have to make the pocket clip. That'll be its own video. I haven't done much on it yet, so it'll be fun to track, to film the whole process of making that pocket clip. But right now, we're making a handle. So as you can see, I've made all these different 3D prints. You know, you print it open, and even though it looks like it's movable, it doesn't move. I just sent the whole file to the printer. You got the handle. I printed these ones on my small printer at home. The quality turned out kind of gross, but it answered the question. So the somewhat most recent design just happened to do this. The flipper tab was just sort of hanging out here in space, and everybody who's felt it here in the shop just goes, that kind of feels unfinished. We got to do something about that. So it's like, okay, no problem. I'll deal with it later. So I'll do it later. So that's what these two were, is just kind of a quick blade open profile and a blade closed profile. And I was able to, I think I didn't change the blade at all. I just changed the handle. So I got the handle to now contour the flipper tab kind of perfectly. And I moved this back a little bit. So as you're feeling it, like, it's a small knife, but it feels really good. And you'll be able to choke up on it here too if you really want to, get in fine and do some stuff. And then when the blade is closed, just due to the design of where the stop pins are and the internal button, I need this groove. And it's hard to do both. It's hard to hide that groove completely and also make it flush with the flipper tab. So we're going to leave it at this. We'll call it a bottle opener. It might actually work pretty good for that. But it feels good, it feels flush. A little snaggy, but I'm not worried about it right now. And then I'm more worried about this because this feels great. And this is like a defining feature that all of our knives have always had. It's got to match there. I realized this designing the integral, and it's got to match here because, so this is with the old handle that sweeps forward this way. It didn't blend here very nicely, and I'm like, wait. Our Rask and our Norseman does, so the integral has to as well. It just has to. So I modified. Now it fits flush from here to here, and then it leads out because it has to get under that stop pin to the flipper tab, so that's fine. But this feels so much better than that. Like, this is unfinished. This is wrong. This is right. And the blades are going to be, we'll see how flush we can make it with the top. There's always tolerance and variation, and when you have a pivot here and a lever, then even a half-degree shift is quite a lot of up and down. But I want it to be good. I want it to be smooth. So 3D printing has absolutely allowed us to visualize and see this kind of stuff. All right, that took 30 minutes. 30 minutes, really. All right, what do we got here? She's looking pretty good. Okay, this radius is what I was expecting on that first handle. That is now correct. Awesome. Excellent surface finish here. Excellent. Okay. It's good, it's good. Yes, that's good. So this one doesn't have any sort of slot yet. That will be coming almost next. I want to actually do some of the holes first. So after our team meeting, I'll get those holes done. And Angelo says this looks like a sphinx. Like there's the head, there's the front paws, there's the tail. I see it. I see it. But it's not going to be called the Sphinx. Even though that is a really cool name for it. Oh, she looked good. She looked so good. Okay, making progress. Welcome to Canadian winters. So part of the fun with prototyping now with a big team, and this isn't even everybody, there's more people that couldn't make it today, is I get to do show and tell, which is fun. Oh, so, yeah. Pass around.
Did you do a finishing pass on the outside? Looks different.
Yeah, the outside's finished now.
Oh, it looks so good. Sweet.
Yeah. So this is the failed first prototype that is wrong enough that I was like, take it out and make another one.
I mean, the finishing looks great.
Yeah. Yeah, it's going to be really cool. But to get your idea around, you know, what it's going to look like, feel like, it's becoming real.
You said what? That's the same as the Rask smooth pattern machining?
Yep. Yeah. Just a lot faster because I've found efficiencies.
Sweet. It's like a trophy.
Trophy of shame.
Next go-karting session.
There you go. Sky, what were you saying about slitting saws? Because I just had a bit about slitting saws.
Oh.
You don't have to say who, but somebody else.
Yeah, a different integral maker
had
a slitting saw basically explode from the feed rate being too high or something, or too big of a cut.
Yeah.
He was just like, yeah, no, I'm going back to doing it the way I used to.
Nice. So either end mill or my way, high feed end mill is great. High feed end mills are awesome. So anyway, just do a little pass around, get some good ideas. All right, so we have finished the contouring the sides, the little radius here for the thumb groove. The profile is finished. The next block of code is, let's look through this. Spot drill, drill stop pins, bore the bottom of the buttonhole, ream some holes, contour some stuff, finish the pocket head, and then chamfering the outside using a trace toolpath, because the surface is not a flat plane surface. It goes up and it goes down, and the trace toolpath allows you to chamfer, having an even width of chamfer all the way around. Otherwise it gets thinner and thicker and thinner and thicker, which can look cool. But for this, I just want to see it like that. So this is the block of code I'm going to post next. All right, here we go. Doing all the holes and stuff. This tool is not pre-called yet because it's the first run of a new program. So it takes another 5 seconds or so to grab it. All right. Spot drill, flip, spot drill again. Literally takes more time doing a tool change than it does drilling a spot. Okay, we got a through coolant. Either 1/8 inch or 3/32 end mill, and it broke. Ooh, interesting. And it's broken. Well, that's how breakage detection works. I don't like that. That means the whole piece is scrap. And then you get a tool breakage tolerance exceeded, and the machine stops and waits for you. I wonder. Okay, my theory, I've already contoured the surface. My spot drill, which is pretty rigid, came in and made a spot, but maybe it didn't make a spot deep enough or something. So when that small tool came in, it didn't have a straight enough spot, so it just got off center or something. That's my theory. So I might want to drill before contouring. I gotta close the door to be able to jog the C-axis. Open the door. What are we looking at here? I mean, I see the spot. It looks fully clean. Let me think about it. So I flipped it around. This is the size of the spot drills from the other side. And maybe that drill was just a little bit bigger than that spot or something. Or I bet you it just kind of went off center. Maybe I should interpolate like a flat floor and then spot and then drill or something. But I don't know if I can save that broken drill bit. I mean, it's titanium, so technically you could etch it in acid, although you're trying to etch carbide down. Also, something I just realized, In manufacturing, there's a million variables to everything, and it's very easy to jump to the wrong conclusions. So in this case, with the broken drill, it occurred to me, what is the tool life of that tool? How many minutes has it been in the cut versus how many minutes do we usually replace it? And it's about 90% worn out with our normal life limit. So that tool was already kind of nearing replacement anyway, so maybe that was a variable. But I do think the contoured surface with the spot that I'm assuming will straighten it is the issue here. And the more worn out tool life means it just might have deflected a little bit worse because of that. So that's kind of where my head's at with that. So I'm probably just gonna have to scrap piece number 2. And the guys are calling it a trophy because of the way it's like mounted on the pedestal. So I got my second trophy here, and then run a third one, and then see where we're at. All right, I have 2 further thoughts on this thing. Thought number 1, that drill bit's not coming out. So I'm just gonna scrap the whole piece and start again. That's okay. Thought number 2, trying to decide where, when to drill the holes versus contouring the outside. Now, when you're contouring the outside, you've got a flat face with a tool that I'm trying to push it as fast as I can while still getting a really good surface finish. And if there are holes in that surface, the tool is going to bounce over the hole and it's going to start to vibrate. And those vibrations will translate. They will down a little bit until it calms down. So as much as I can, I like to contour when there are no holes yet, because especially the faster you go, you don't want to make it artifacts. And they may only be like just a little bit past the hole, but it's something. So I'd like to avoid that if I can. So I'd like to do all the contouring on a smooth surface and then drill the holes. So I got to figure out a way to like maybe end mill, interpolate a flat feature, then I can spot, then I can drill, and then you have a perfectly square, perpendicular drill, as opposed to trying to spot on a curve and then assume your drill is going to follow that too and nothing's deflecting. I think that's where I'm at. Here's a visual of what I'm talking about. So this is my spot drill. The surface is not that curved. I'm pretty sure that the spot drill will be square, but like strong enough to not deflect. But you can see it leaves a very non-centric feature. And then if I drag, here's my drill, my 1/8" drill. I mean, according to the simulation, this should center perfectly, but it didn't. It broke. Now, it was also a worn out tool, but it's also going like that. I don't know where it broke at the bottom. It was through coolant, so it should deal with the heat no problem. I'm not sure. It's also drilling a lot deeper than it normally does. Normally we're only going through a little blade like this or a handle. So I'm not sure. All right, I'm replacing this broken drill bit right now. We use these OSG A brand drill bits. They're a through coolant drill bit, which means it literally has 2 tiny little holes going all the way through it, matching the spiral of the flutes, so that coolant comes out the very tip where all the action is happening. We keep them in our drill holder here. We've got reamers, drills. These are little through coolant drills. This is the one I just pulled, which means we have 1 left, which is not enough. So I'm gonna order some more. So when I'm done, I put the bin with the label in this order more bucket. And then when I have ordered it, they go into the I have ordered it bucket. So just a little visual cue for us. I will order more of those. Okay, let's get under the microscope. I want to show you guys the drill bit here. It's really cool. Back to the Zeiss microscope. Yeah, so it's got a camera on top. The camera goes through one of the eyepieces, so when the camera is on, one of the eyes is visible and one is black. Like you can see through that one, but you can't see through that one. But if I flip the little flippy in the back, now the camera shuts off and now I can see stereoscopically through both eyepieces. So I'll show you quick and dirty. This is what the drill bit looks like. It's an 1/8" diameter and those holes go all the way through. If I flip the drill bit over, you can see in the gash back there are 2 entry holes where there's a sealed collet that doesn't let coolant go around it. So all the pressure coolant has to go through there. It could be up to 1,000 PSI on the kern. Super cool. And then the broken tool is right there. Let me focus on that guy. And you can see the 2 spiral holes that are formed all the way through the drill bit. Really cool. So this is what we call progress. 2 failed attempts, but I learned a lot and I made a lot of progress on each one. And now hopefully the third one can go off without a hitch. I've made some changes to the drilling cycle, so I've got everything dialed in. It's a little challenging because the surface is curved. I struggled a little bit. That's good to go. Unfortunately, my time is up for today, and I will come tackle this. It's the weekend coming up. Maybe I'll squeeze some time this weekend to come in and finish up this handle because, dang it, this video is going up on Tuesday. Knifemaking Tuesday is back. So, super fun to get back into it. Super fun to develop a new knife. I'm having an absolute blast. Even with the challenges and the struggles, I like this. I thrive in this. It's fun. I like it. Okay, I'll be back. All right, back at it. It is still Friday night. It's about Longines o'clock, 10 p.m. Friday night. This is where I want to be. I've got prototyping on my brain. I'm sitting at home trying to relax, and I'm like, no, not happening. I got to get back to work. Later, honey. I'll be home tonight. And she said be home before dawn, so I have my time limit now. So anyway, I have my third handle. I've roughed it out. I've surfaced the sides. I figured out a trick with surfacing. I was trying to be all fancy with the first 2 by making smooth pattern, which takes a decent amount of time. One of our knives, the Rask, has a streamline pattern, which is like the roughing pass for smooth, but done really well, and saves a lot of time. So for this prototyping stage, I can save many, many minutes just by leaving this super bumpy, but still extraordinarily beautiful streamline pattern. So for proto, that's awesome. So if you remember, 5 minutes ago for you, breaking a drill bit in, not this hole, the other side hole, but one of these holes, no bueno. So because this surface is contoured, you know, I thought a lot about what could be going on. I was driving home, driving my kids around, thinking like, man, what could it be? One thought that I had was maybe the flutes of the drill bit are not long enough to go through this much thicker material than we're used to going through. And for a while, driving around, I'm like, that's it, that's gotta be it, because these are 3 times diameter drill bits, and I normally only drill 1/8 inch deep, which is 1 times D, and this is a lot thicker material. But then I come back to the shop and I confirmed that that's not true, that the drill is plenty long enough to get all the way into that hole. Okay, so I'm still leaning towards the contoured surface being a problem. So what I did is I took a little flat end mill and I contoured, or I did a bore tool path and I made a little flat. And then on some of them I can come in with the spot drill and I can peck it. But some of them I can't without causing a bigger chamfer and looking weird. So I also have in the machine a flat bottom drill bit, which I think is right here in the spindle. This is a flat bottom drill bit, shaped almost exactly like a regular drill, except obviously flat on the bottom. So not an end mill, it is still a drill. And we use this to clean up the bottom of a drilled hole. And that's exactly what I'm doing here to prep for the full-length drill that goes through. So these holes, I spotted them, I bored them with a little bore tool path, and then I came in with the flat bottom and I went down just a little bit, so that when the through coolant drill bit comes in here, it has a guide hole to kind of keep it in line, and then there's no spot on the bottom of the hole, but at least it's guided, so it should be able to just do what it's got to do. That is the very next tool path, so we shall see. Here we go. Remember, this is the first cycle, so it's still got to catch that tool. It's got to grab it from the rack. Takes a couple extra seconds. Doesn't have it pre-called. Should be set to touch off because I haven't used it yet, or not. I was confusing myself there for a minute why it didn't touch off, because I replaced that a couple hours ago. The machine's been running since then. It auto-touched off already. It already has half a minute of tool life drilling tiny little holes. So it did the hole, it drilled it, it's good to go. Good. Let's continue. So this is going through the flat bottom drill bit. Oh, shoot. The first hole worked, the second hole snapped halfway through. Ah! You can actually see it. I lost it. You can see it peeing 2 streams as it still had some pressure. Man, first hole worked great, second hole didn't. Okay, the other variable that occurred to me is if theoretically the stock is moving, that tiny little drill bit, I don't see it moving this stock, but that could be an issue. If it moves the stock, then everything gets crooked, and then deeper into the hole, the drill just kind of goes snappy snap. Kind of neat that we can see all the chips here. We could actually collect these and inspect them under the microscope if we wanted to. That's kind of interesting. So on that line, I wonder, these vice jaws are awfully close together. I am curious if they're bottomed out, or if they could go more. So I should probably measure that gap now that I broke a piece. Measure that gap now, take the piece out, clamp them down all the way, see if it does clamp more. Because maybe I'm bottoming this out, I'm not holding the stock as rigidly as I should be. Maybe it's causing just enough vibration, movement, whatever. That could be something. But darn it. First hole worked great, second hole didn't work great. And it wasn't at the top. I heard it go in, I saw it go in, and then it snapped kind of more near the bottom. So under the microscope here we have the chips that just came off that drill right before it broke at the mere seconds before it exploded. I don't know a lot about reading drill chips, but I know they can tell you a couple things. So if we look here, we have some pretty nice, short little chips, which means they're breaking and exiting, not creating long bird's nests. That's really good. We have this chip over here that is squishing itself. I don't know if that's good or bad necessarily. There's a couple of those that are squishing. But these are titanium chips too. Notice how they're, lost it. Notice how they're shiny on one side and dull and matte on the other side. That's kind of what a drill bit just does. Kind of cool. I don't know, I think they look good. Maybe this packing chip might tell me, if I knew a little bit more, if it's packing up, maybe I need to feed faster or spin faster or something to prevent that, because if those little boogers get stuck at the bottom of the hole, in a relatively deep hole for the small diameter, then they can't evacuate and then the tool could break. So maybe that's what happened, I don't know. Maybe I should be peck drilling, even though with through coolant you usually don't have to, you just plow right in. And also I've got, I forget how high pressure this one's set to, but many hundreds of PSI. Evacuating all the chips and cooling the cutting zone. I don't know why it broke. Or maybe it's a rigidity thing. Could be so many things. I gotta figure it out though. Fun fact, each of those drill bits is about $80 Canadian. And the piece of material, the chunk as well, ain't cheap either. As the cost of prototyping and R&D, I'm running low on those drill bits, so I can't keep blowing through more of them. But that's where I'm at. Here I've got my little set of gauge pins, my 11 thou to 60 thou. Each one's got a little protective cover on it. Tiny little precision pins in 1 thou increments all the way down to whatever. So I'm gonna figure out what that gap is between the two jaws, take the stock out, squish them all the way, and we'll see what we get. .26 thousandths of an inch is the answer. Now, we shall remove scrap piece number 3. I totally forget that I'm wearing a mic and I don't have to stand right next to the camera to be able to talk to the camera. I don't even have to look at the camera to be able to talk to the camera, and you guys can still hear me. That streamline pattern looks pretty tasty. But that broken drill bit doesn't look so tasty. That hole drilled great. This hole drilled great. 1/8 inch hole on this side, 3/32 on this side, it broke. All right, the jaws are fully tight. It looks like less than 26 thou, but not by a lot. Let's try 17. Yeah, it's thinner than 17, which tells me that we're fine. Not by a big margin, but I don't think this is the problem. Yeah, even 14 doesn't fit. Jumped down to 11, which is like 11 does fit. It's probably 11, maybe 12. So that tells me 26 thou, 11 thou. Not a lot of squish of potential over travel, but I think it's gripping the stock well enough. I really need to stretch out those dovetails more so that there's more potential grip. It's not ideal in this scenario. I don't think that's the problem though, which means I don't know what the problem is. And you know, everything we do is about consistency and process reliability. And break and drill bits is not process reliability. It's no fun. Honestly, I'm kind of surprised. I did not expect breaking drill bits to be the annoying part of this project. That does have me a little thrown off. Here's our broken drill bits. Through coolant holes and all. Okay, this is interesting, maybe possibly. Look at the bottom of that hole. That is a lot of chips trying to make their way out, is it not? Maybe we do have a chip evacuation problem. This hole, let's see, it's a 93 thou hole going down maybe 380 thou. So it's almost going down 4 times diameter. Through coolant, maybe I gotta jack up the pressure of the coolant. Let me check right now. I can look this up. Since I'm recording on Elgato, I'm going to change my screen and I'm gonna record. Anyway, this is VNC, which is remoting into the kern. Tool 134 is my 09375 drill. And it's locked, L for locked because it's broken. 120 minute life, only 11 minutes on that drill, suck. This one parameter is yes, coolant on, and coolant pressure should be 40 bar. So 40 bar out of a maximum of 80 bar 1000 PSI, it should be 500 PSI going through that tool. I could absolutely jack it to 80 bar 1000 PSI. I'm sure that will help. I should do that. Okay, this is progress. Clearly, all those chips are not leaving the hole, or they're working their way out, but how stuck in there is that drill bit? Is it moving? I can't tell. I don't think it's moving. I think that's just perspective. Just because I'm going to try to get this out with my pliers, and I think I saw it move. And if so, I want to film it. It did move. Look at that. I might actually get this guy out, which might help. Yeah, it'll help. It'll tell me if the whole hole's packed with chips. It'll tell me if the end of the drill bit is shattered into a million pieces or if it's like fine. Just gotta figure out how to hold this thing. That is absolutely moving. I think it's just held in place by the chips that are stuck in the hole. Get a good grip on it and leverage my way up. Here we go. Okay, this is something. All right, one more little thing on this drilled hole, and then we'll move on. So I blew it out with air, and as you can see, there are some chips kind of. I don't know if that kind of chip can evacuate properly. Maybe I should send this video, this little clip to OSG and be like, just what do you guys think here? Is this, what am I doing wrong? I think for now, I'm just going to peck drill that hole, which I've heard from Saunders and I think somebody else, you're not really supposed to do that with through coolant drill bits. I don't really know why. I think it shortens the life of the tool. Every entry of the hole is the hardest on it. I don't care. So I'll do a deep drilling cycle on this, and that's probably going to solve it because it's going to clear the chips away. I think that's going to be fine. At least that will save the, what do I have left? I got 2 of those drill bits left, and we need this for production. No questions, whatever. I cannot go down to 0 because otherwise the current is dead until we have more of those drill bits, which could take a day to 5 days. So that's not acceptable. I'll get it. Here we go for test number 4. So basically machining everything up to and including the new peck drilling cycle. And I'm just gonna, I got other stuff to do for the however many minutes it'll take to basically get to and past this stage, a couple tool paths past this. If it breaks a drill, I don't need to watch it break a drill anymore. So I was in the kitchen having a snack, just letting the machine run, had the door open, I could hear it, I could hear each tool, I could hear the screw spindle cool. I was like, it's good, it's good, it's good. I let it go. It's still going. It got through all the drilling. We're on to the next steps. It's just about done all these tool paths, and then we can post the slot again. Or not again, the first time. Success. So far, success. Those holes are drilled and reamed. That hole is drilled and reamed. That's where the button lock is going to go, the button. This is for the pivot. And then on the back side here, we have 2 stop pins. All of our knives have 2 stop pins. This one's just going to be unique, different. Everything is chamfered, the outside's chamfered. I didn't have quite enough clearance here for the chamfer tool. So in the future, I'm going to have to thin out that web before the chamfer because the chamfer kind of dug into that web still. So I had some clearance issues there. It's harder on the chamfer tool. Okay, next is the slot, and then a couple internal features, and then a couple fine touches. I got a thread mill at the top of these holes and fine tune that. And then once all that's done, we'll chop it off. So when I talk about cutting the slot with a high feed end mill, this is one example of what I'm talking about. So this is a helical high feed end mill, about, what's the size of this one? I think it's an 1/8 inch diameter. Tapers up a little bit at the top. It's got a weird radius at the bottom. Not a full radius, just kind of like a shallow taper. And you're only cutting down, I'm zoomed in a lot right here. This tool is only about this wide normally. You're only cutting down about, what, 6 thou, 9 thou, depending on the size of the tool. And that pretty much, even for such a long tool, does a really good job of putting all the cutting forces this way instead of this way. And that's what's so cool about high feed end mills, is even though you're just zipping, zip, 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 you're not putting as much bending load as you would with a traditional end mill that's just cutting straight from the side. Because of this radius, you're kind of forcing the energy this way, which is just brilliant, especially for long, tiny, tiny end mills. It's just super cool. So the theory is use this whole end mill for the whole slot. I've done a partial slot to test it out, but I haven't gone all the way down yet. Okay, so if we do a quick simulation with tail toolpath turned on, you kind of see what's going on here. And I actually had to draw a toolpath that goes zigzags exactly within the range of what I want, and that took a while, but I think was worth it. If I turn on the full toolpath, you see what that looks like. So it zips here, and then it zips there, and then it goes all the way across. Here we go, boys and girls. Sounds pretty good. Going at 99 inches per minute, 9,000 RPM. Sounds a little chattery. This is the helical end mill. The De Boer end mill just sounds angry when it does this, but like in a good way. It rips it quite a bit harder and faster. So it should be almost done with the rightmost section. Then it'll lift up and do the leftmost section and then match them and go all the way across. The cool thing with this is like spindle load is nothing. Just the RPM of the spindle being on. There we go. All right, we'll let that go. As that thing is zipping away, had a thought. I made a post about this on Instagram just now, a couple hours ago, and a bunch of machinist guys were like, use a slitting saw, use a slitting saw. And I've already said my thoughts on slitting saws. I've never really used one, so I can't say, but to reach the geometry, the depth of this handle, maybe not this one, but I guess in my head I was thinking Norseman, what I'm about to say, like back in the day. You need basically a 4-inch slitting saw to get at least an inch of depth on the one side. And you got your arbor, and then you got the whatever. At least that's what my brain tells me. And that's the Sandvik one that I bought. It was like 4-inch. It's about like yay big. The Kern can't even touch off a 4-inch tool. I think not even a 2-inch tool can fit between the laser centers. So that's another reason why I don't want to put a slitting saw on the Kern. And the HSK tool holder has no drive dogs, so it theoretically could slip within the shank. Let me grab one just for explanation. This is an HSK holder. There is nothing keeping it rotationally from slipping. However, something like a Speedio, this is BT30, has these drive dogs with literally metal dogs that prevent this from spinning to the spindle taper. So this is technically more spin resistant, rigid, than an HSK is. So that's another reason I don't want to put a slitting saw in the Kern. I could do it in the Speedio, I could do it in the Mori. I just don't want to do it. I want to do one and done. I want to do 5-axis, one and done part, leaving a tiny little tab on the bottom that our expert finishing department can deal with and make perfect. That's the vision, like I talked about earlier. That's my shoot for the moon. That's what I want to see. I want it like that. I could do it 100 different ways. This is the way I want to do it, and I want to see it through. And maybe it sucks, and maybe I'll do it a different way. But so far, aside from some broken drill bits, so far she's working. Taking a closer look, let's see if I can get it on camera. The surface finish on the inside is definitely rough and chattery. However, the floor finish looks sick. And this is rough. This is a roughed finish. The floor finish looks very scalloped because the tool zipped, like if you go do a side view, it went zigzag down. So it's got these bunch of concentric rings, scallops looking down. That will get cleared away, but it does look really cool. And the inside finish, it is rough and chattery because the tool is so long, and it's like marginally okay, but we're gonna make it even prettier here. If all I had was the 3-axis mill to go in with a high feed end mill and slot that out, and if I were somebody else, you could almost just send that inside finish. It's not great, but it's pretty good. And the floor finish looks really sweet, and it lets you get all the geometry you want. I think high feed end mill's a total win. Next step is to take this long tapered ball, and I want to surface the inside just like we did the streamline pattern on the outside. So the ball, if you notice, is tilted at 1.5 degrees that way because Kern, because 5-axis. And I want to get a really nice surface finish on the inside. And it's going to be stepped. That's okay. I'm fine with that. But it's going to be a lot shinier and nicer than the high feed end mill. And more importantly, it's going to get me the width that I actually need. because the high feed is only, what is it, 1/8 inch, and I need the slot to be 150 or 156 or whatever it is. So this lets me surface it to the thickness that I want so that the blade actually fits inside. It's going. Sounds a little singy, but that is a very long tool. You can just see the 1.5 degree tilt. There it is, B negative 1.5. I'll turn the coolant back on in a second here, but I gotta show you guys. So I'm booking it. I'm doing a pretty big step down too. And it's an inside feature. It doesn't need to be as pretty as the outside. So we'll see if it looks a little chattery or not. I don't know yet. It's happening! Oh, this is so exciting. Literally 11 years. I can't even tell you guys. It's like, dude, when I designed this knife, all we had, 2011, we didn't even have a Tormac yet. No, 2012, I designed this knife, late 2012. So we did have the Tormac, but it's just crazy. I can't believe it's been so long. So much has happened, so much has changed. It's amazing. And like now we're in a position to do this, to make it, not just to make one, but to make lots, not millions, but make a good amount. And I'm using all of my knowledge and all of my skill and the team as well. We're leveraging everybody to not only make it designed for manufacturing, to make it like faster, because we know the demand is going to be right up there, which is amazing, but also to, you know, make the tool paths look really good, make the tolerances as the best we've ever made. It's like gives us the chance to start from scratch and make a new knife with all the skills we've learned over the past 12 years of making knives. It's so cool, so cool. And the other thing is, it's not just another folding frame lock flipper pocket knife. It's a flipper, but it's a button lock, and it's an integral, and it's the smallest knife we've ever made, and it's just fancy pantsy. And I love it. And it's got some new technologies. The stop pins are going to be a little bit different. Add some challenges, some struggles. Honestly, I don't even know if this knife is going to go together properly. The button lock, is it going to be smooth? Is it going to rub? Is it going to drag? Our other knives have a ceramic D10 ball that we flatten, we diamond polish. They're super smooth. I don't know if this knife is going to be that smooth. I kind of think it won't be, but I won't know until I put it together. So that's like one of the gambles. You can see how deep that tool is going. It's in there. All right. And I'm doing a quick finish pass on the bottom contour. Should really have the coolant on for this. So this is finishing up basically the floor of the slot. 3 passes, stepping down a little bit every time. All right, that tool path is done. It's hard to see, especially on camera. I think it looks okay. I think it looks a little chattery. It does look a little chattery. Okay, I'll play with that over time. I don't really care right now. It didn't explode, so I'm good to go. Maybe I'll just slow it down next time. I don't know. Next up, we have this tool here, which is a custom designed by me, custom made by Harvey Tools key seat cutter. And its goal, which I'm just about to find out here, kind of nervous, is to go through the pivot hole and cut the bearing pocket on the bottom inside lip of that handle. So let's find out here. Whoa, slow, slow, slow. I mean, simulation said it's good, but I'm still nervous. turn the coolant back on because it just needs it. I made another little goof. This is a piece of broken end mill. So the clip will mount in a little slot that gets put here, and there was supposed to be a 2D adaptive toolpath that gently nipped away at all this material, but because the model changed at some point and the sketch contour changed, it just plunged right in. So I'm trying to pick this end mill out. Hopefully I can save it. If I can get all the carbide out, then I'll run it again. If I can't, then this handle might not be so happy. Luckily, these end mills are cheap. They're like under $10 each. So even if I destroy the next end mill to try to clean this up and get that piece of carbide out, I'm kind of okay with that. It's like every time, this is handle number 4, every time I make another handle, I get so many more % done. This is literally 92% through all of the programming, like right near the end, just a few more tool paths. But the good thing is I've now proven and error-proofed 0 to 92%, whatever that number is. And now I'm just on the last little bit. So like, if I do scrap this handle, I could pretty confidently just run the next one up to this point and know that it'll be good. And I fixed this change already. So this is the cost of progress. You want to see a cool tool path? Check out this tool path. This is like the ultimate 5-axis. I've already proven it, so I'm gonna run it at full speed here. First time running it at full, actually. Turn the coolant off. Yes. Maybe it's just me who's puckering so hard, but it works. It was kind of scary to watch. That's very cool. That's the deburr toolpath in Fusion. It's working. You can see the glint of the chamfer on the back wall there from the deburr toolpath. It worked out great. Okay, so I still have the piece with the broken carbide at the clip slot. However, I decided instead of scrapping it at 92%, let's skip ahead and finish up some of the things like that deburr toolpath I just did. The pivot bore was a little bit undersized, so I opened that up. I got the thread milling nailed. That took a bit. And I think I'm gonna actually finish and cut off the bottom of this. And then on the next one, I should be able to do that properly and all the cutoff and everything will be done. Now I have removed even more material. I finished the back wall. I deburred the slot leading inside. So now all that's left is this is a 20-inch curvature, 20-inch radius curvature. So all the little turns and flats and everything are done so that once we tab this off, the guys in the finishing are just left with a curve to finish up nicely. So the theory goes. So now I haven't programmed this yet. I got to figure out how to tab that off and make it half decent. The last step is to tab it off. So I ended up drawing a sketch to define where those tabs are, and then I made them I think 20 thou thick to the point where I can rock it back and forth until the material gives way. I got one side off, now I got the second side off. So that bottom face is like semi-finished. Yeah. Whoa, I'm holding an integral handle. Whoa, weird moment. It's actually kind of heavy. It's like heavier than I thought. Because I guess our normal handles don't have a solid back spacer. They're just two little spacers. So that whole chunk is not there. And then the Rask handles are lightened on the inside, so they're quite a bit lighter than these are. It's got some good heft to it. Curious how that's going to be with the balance of the knife. I don't know. I'm holding it. Okay. Still some things to tweak. It's 3:30 in the morning. I'm fried. I'm going home. I might grind these off and like put this in my pocket for the weekend, but that was a lot of work. After weeks and weeks of getting to here recently, and years of thinking and design and picking at it. It's so cool. Super cool. Here we go. I did an okay job, not bad for rushing on my first go with not our best, deburring equipment. That's in the front shop. I just want to put this in my pocket for the weekend and stop thinking about it, or I'll keep thinking about it. I don't know. It's almost 4 o'clock in the morning. I'm done. It's heavier than I expected. Kind of surprised. I don't know why that surprises me, because it totally makes sense, but oh mama. Okay. I think this tells me that the next one will be perfect. Yeah. I think that is what it tells me, which is really cool. Like perfect-ish. Perfect as in no mistakes, and then there's further refinement after that. Because I've made all the mistakes on this is now the 4th piece. Not bad. Got it on the 4th try. A lot of fine tuning left to do, but cool. Man, okay, wow, okay. How about, let's wrap up Knifemaking Tuesday Reintegration 01, whatever we call that. There, because otherwise this will never end. Awesome. Okay, more fine tuning to do on this. Next big project is the blade. I gotta make a fixture, I gotta make clamps, I gotta design how I'm gonna do the cam. Very similar to how we do the Rask blade. I'm actually gonna use a Rask blade blank, because we have hundreds of them. So I'm gonna do that. And then the cam for that, and then test that. It's more work than it is like new, weird project. So that's not so hard. And then I've got some Williman projects. Like I said, the stop pins, the button, and then start slapping it together and see what's next after that. And then the clip, we'll leave the clip till the end. Dude, bro, done. Knifemaking Tuesday. Welcome back, everybody. All right, I'm going to sleep. Bye-bye.